This problem is to solve the melting ice ball problem using proportionality, sphere geometry, and the chain rule for linear radius decrease. A solid ball of ice is placed under a heat lamp and begins to melt. The rate at which its volume decreases is directly proportional to its surface area. The ball stays perfectly spherical as it melts. Suppose the initial radius of the ball is capital R sub 0, and after 2 hours, 5/6 of its volume has melted. How many total hours will it take for the ball to completely melt? Let's walk through this carefully. First, since we're working with a sphere, we know that the volume of the ball depends on the cube of its radius, and its surface area depends on the square of the radius. Now, we're told that the melting rate, meaning how fast the volume decreases, is directly proportional to the surface area. So we can model this by saying, the rate of change of the volume with respect to time is equal to negative k times the surface area, where k is a positive constant. But we can also express the volume as a function of the radius. If we differentiate the volume with respect to time, we get an expression that involves the square of the radius times the rate of change of the radius. So we equate those two expressions, one coming from the chain rule and one coming from the proportionality with the surface area. When we do that, we find that the square of the radius times the rate of change of the radius equals negative k times the square of the radius. Since the square of the radius appears on both sides, we can cancel that out, which leads to a very nice result. The rate of change of the radius is simply negative k. That means the radius shrinks at a constant rate over time. So we now know the radius is decreasing linearly. We can write the radius as capital R sub 0 minus k times t. Next step, we use the information from the problem. After 2 hours, the ball has lost 5/6 of its volume, which means it only has 1/6 of its original volume left. We substitute the radius at time t equals 2 into the volume formula and set that equal to 1/6 of the initial volume. Since the volume depends on the cube of the radius, we're really saying the cube of the radius at time 2 equals 1/6 the cube of the initial radius. So we plug in capital R sub 0 minus 2k in place of the radius, cube it, and set it equal to 1/6 of capital R sub 0 cubed. Taking the cube root of both sides, we find that capital R sub 0 minus 2k equals the cube root of 1/6 times capital R sub 0. Now we solve for k. Subtract the right-hand side from capital R sub 0, divide by 2, and that gives us k equals 1/2 times capital R sub 0 times the quantity 1 minus the cube root of 1/6. Next step, we now want to know, when does the radius reach 0? That will be the moment the ball has completely melted. We go back to the linear equation for the radius. Radius equals capital R sub 0 minus k times t. We set the radius equal to 0 and solve for t. That gives us time equals capital R sub 0 divided by k. Now plug in the expression for k we just found. The capital R sub 0 cancels out, and we're left with time equals 2 divided by 1 minus the cube root of 1/6. Now we just need to estimate the cube root of 1/6. That's about 0.1817. So 1 minus that is about 0.8183. Finally, 2 divided by that is approximately 2.45 hours. Whenever you're dealing with geometric shapes that shrink or grow while keeping their shape, it's really useful to express both volume and surface area in terms of the radius. Then, use the chain rule to link how the volume changes over time to how the radius changes. In problems like this, the rate often simplifies beautifully, like it did here with a constant decrease in the radius. That makes the rest of the problem much more approachable. That's it for this question. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel. If you're looking for tutoring on final exam level questions, check out my YouTube channel at MathTutor8285. You'll find helpful explanations and strategies to ace your exams.